Now we're going to work with seasonality to see if we have seasonality in the data, how do we handle that in our forecasting. Many industries have seasonal variations in demand, which is a pattern of ups and downs that repeats itself. The length of the seasonal pattern, we will refer to that as M, i.e. M time periods. The pattern will repeat after every M time periods. With quarterly data, you may have what we call quarterly seasonality, where M equals 4. So every 4 quarters, the sales pattern repeats. So that is why you'll often see in financial news reporting or industry news, they'll say the sales of this industry or this company is up by 10% compared to the same time last year or compared to the same quarter last year. So that is, if sales has seasonality, you can't just compare the sales of one month with the previous month because the seasonal pattern is influencing the sales of different months, and that's not going to show you the growth. But if the sales in November compared to last November are up, that means this year is going better. Or sales in quarter 3 compared to last year's quarter 3 are up, that means this year is going up. So comparing month to month, the same month this year to same month last year, quarter to quarter, that's often done when you have seasonality. Now with monthly data, you often see a 12-month cycle. Every 12 periods or every 12 months, the seasonal pattern repeats itself. With day of the week seasonality, you can go from Monday to Sunday and then Monday to Sunday again. So maybe weekends have a higher sale or demand than weekdays. And sometimes if you have hourly data, they can even be hourly seasonality. Imagine you are a cafeteria in a large building and a large office building. You may have hourly seasonality where the demand goes up a lot in lunch hour, maybe in the morning when people arrive, but then there's some hours where the demand is very low. It's usually easy to find M because you just know from the context, or you can just plot the graph and kind of see where the peaks are and how far apart the peaks are. And if the peaks always occur 12 months apart or 4 quarters apart or 7 days of the week type apart, you kind of know that's the period M after which the seasonal pattern repeats. Now we're going to first look at the regression method because it's very flexible and very easy to use with seasonality. What we do with regression is we've already seen the regression for trend, which is yt equals b0 plus b1t. So this first part of the regression equation we've already seen, that's capturing the trend. But then we extend the regression to include other variables, and we put in a variable for each time period for which the seasonal pattern can repeat. So if you have quarterly data and M is 4, you'll put in dummy variables for quarter 1, quarter 2, quarter 3, quarter 4. Actually, well, you'll eliminate quarter 1 or quarter 4. You only put 3 quarters. The reason you only put 3 quarters is because if all of your, let's say you have quarter 2, quarter 3, quarter 4, if all these quarter 2, quarter 3, and quarter 4 variables are 0, that means it's quarter 1. So to capture 4 levels, quarter 1 to quarter 4, you only need 3 binary variables. A binary variable can only be 0 or 1. It's like a flag which indicates whether a condition is true or not. So if quarter 2 is 0, so the flag is saying it's not quarter 2. Quarter 3 is 0, so it's not quarter 3. And quarter 4 is 0, it's not quarter 4. So you don't need an extra variable to tell you it's quarter 1. Obviously, it has to be quarter 1 if it's not quarter 2, not quarter 3, not quarter 4. Same thing with monthly data. You have 12 months in a year, so you're going to use 11 dummy variables, either January, February, March, April, all the way to November, so January to November, or you can eliminate January and have February, March, April, May, June, July, all the way to December. Okay, and when all these variables are 0, then that is the month that was excluded. So what do these variables capture? These variables capture the effect of each month compared to the excluded month. So B2 times February captures the change of the sales in February with respect to the sales in January. So if February is a slower month than January, then B2 can be negative, showing you that sales in February fall compared to January. If February has higher sales than Jan, then B2 can be positive, showing you that compared to January, This is the increment in February sales on average. And then you have the error term, and you can estimate this regression equation in Excel, and then you can use that to forecast. Okay, so the example I'm gonna show you an example with monthly data of how to handle seasonality. Before we get to that example, I want to show you that in a regression model like this, where you have y equals b0 plus b1 times time plus b2 times dummy variables or binary variables to capture the different time periods, what you are doing is you're modeling seasonality in an additive way, because what you are saying is for any given month, the sales can be plus or minus a certain amount. Like if B3 is 10,000, then sales in March are 10,000 more, right? The other way to model seasonality is multiplicative. So what does that mean? In a multiplicative seasonality, you are saying that the sales are higher or lower in a particular month compared to other months, or a particular quarter compared to other quarters, as a percentage amount. For example, if demand in November is 40% higher than the average level, you might have a seasonal factor called of 1.4. So you can say, okay, average sales is 1,000. So for November, my sales are going to be 1.4 times 1,000 or 1,400. Now, if your average sales fell, and now let's say you're doing on average 800, then the sales on November would also fall, because the new November sales would be 800 times 1.4 or 120 instead of 1,400. The additive seasonal method just says that the demand goes higher or lower by a certain amount. So in the additive seasonal method, if your demand in August is 200 units less than the average, so it's like B of August, the regression model is minus 200, that shows August is 200 lower, then if your average sales was 800, August would be 600, 800 minus 200. And if your average sales was 1,000, August would be 1,000 minus 200 or 800. In terms of a regression model, you'll not look at the average sales, you look at the sales for the month that's missing from your binary variables. And you'll say, okay, if January was missing, then all the different months are compared to January. So if August is minus 200, that means August is 200 lower than January in sales. Now, whether your sales in January increase or decrease, the difference between August and January stays at 200. It's not increasing, decreasing within the level of sales. Whereas in multiplicative seasonality, it does increase or decrease with the level of sales. So you can ask yourself this question: if your company's sales grow, are your seasonal peaks and troughs going to get bigger? If so, then you need a multiplicative seasonality model, such as the Holtz-Winter model we're going to discuss next. You can also be modeled with regression, but in a more complex way, we're not going to cover. We're only going to cover additive seasonality with regression. And so you have to model a multiplicative seasonality model, where if the average level of your sales grows, the seasonal peaks and troughs also grow. But if you feel that as your average level of sales is growing, your peaks and troughs, like their height compared to the average level, is not growing, it's approximately the same, then you can use an additive seasonality model. Okay? So let's use an additive seasonality model to estimate an equation like this using regression. Here's our data. It's sales on 10-ounce shampoo bottles for the past 5 years. And I only took 4 years of data, and I saved 1 year of data as a holdout sample. And we'll talk about that towards the end of this lesson, about why do you need a holdout sample. You must have seen even previously, I kept 6 months of data as a holdout sample when I was doing forecasting with trend, like the Holtz method, because you want to develop your forecast. Based on some data, but then you don't want to evaluate the performance of your forecasting model using the same data. I mean, you can forecast these first 4 years, get MAD and MSE, but because you're trying to estimate the coefficients based on this data often your regression model or whatever model you're using will fit this data really well and show you a very small MAD or MSE. But when you apply the model to new data that the model has not seen, your error will be usually a little bit larger or the same level or a little bit larger. So if you would overfit your training data or the data you're developing your model on, and you customize or estimate your model to really fit this data really well, you might end up fitting the noise in the data that's not going to repeat in the future. And then on your holdout sample or future values on which, or when you actually use the model, you're going to have high error rates because the noise does not repeat in the future. Only the signal part of the data repeats in the future, because signal is the repeatable patterns. So you want to avoid overfitting, and the way we avoid overfitting is we leave some data as a holdout sample. We build our regression model or whole swinter model on the training data, and then we apply that model to the holdout sample, and that's how we figure out what our MAD and MSE are and how good our model really is. If you overfit to the data here, your MAD and MSE will be pretty bad in the holdout sample, and there'll be a big difference between MAD here and MAD on the training data. But if your MAD MSE values are close, they're not too much worse on the holdout sample, then that means you've not overfit the data. So that's why we use a holdout sample. Okay. This is the plot of this data. So shampoo sales, you can see the seasonality. They peak about the same time each year. And you can see that if you do just a trend model, this is a regression equation, which is B0, which is this, plus B1 times T, where T here is called X. That's just the name of the variable it gave when I plotted the data, but this is actually T. Okay. And so B0 plus B1 times T, this is the model with just trend and no seasonality. And you can see we don't get a very high R-square value. R-square value is even below 0.5. So 0.33 means only 1/3 of the variability in the data is being explained by the trend, and 2/3 of the variability in the data we're not explaining. That's because their seasonality in our model is too simple. Okay, so how do we do this in Excel? So what we're gonna with regression, what we're gonna do in regression is this is the same data, okay, data on monthly sales of 10-ounce shampoo bottles, and what we do is we have the month and the sales. So we create the time variable like before, which keeps going up. It doesn't wrap around after 12. It goes to 13, not 1, right? So we get a time variable like that. So we create this time variable, basically 1, 2, 3. If you type 1, 2, 3 and you drag it down, Excel automatically fills it by incrementing the number, and you just drag it down all the way. And we took 4 years of data, and we saved 1 year of data as a holdout sample to test our final model. In any case, so you have time, you have sales. What you want to do now is whenever the month is 2, you want to set the February column to 1. It's a binary variable, which is 0 or 1, and it indicates when is it the month of February. So if it's 1 here, this was February, that is correct. It's 1 here, this was year 2 February, that is correct, and so on. So how do I generate this variable? I just type an if condition in Excel. So if the month value is 2, give me a 1, because it's a flag that goes up if the condition is true. So yes, we are in February. But if the month is not equal to 2, then give me a 0. So this is how the if statement works. You type if in Excel in the formula bar, then you select the cell you're going to compute on, which is the month, and then I'm going to put a $sign just in front of the B, not in front of the 8, because if I drag the formula down, I want it to go to B9, B10, B11, B12, B13. But if I drag it horizontally for the March formula, I want it to still work on the month cell, because all of these variables, February, March, April, May, June, July, they're all built on the month column. Anyway, you don't have to worry about the $sign. When you go to March, you can just type, cell B8. Anyway, what we're looking at is B2 equals 2. Is it equal to 2? Is it February? Then give me a 1. If the condition is true, it returns the first value after the comma. And if the condition is not true, it returns the second value, the value after the second comma, which is 0. Okay. So it's saying we don't do equals in Excel, we just do equals. If B2 equals 2, give me a 1, otherwise give me a 0. So that's how you type in the formula, and then you can just drag it down. Okay, and they'll just tell you with the 1 whenever it's February. For March, we do is if B8 equals 3, give me a 1, otherwise give me a 0. So it'll always give you a 1 whenever it's the month of March. Okay, same thing for April, May, June, July, up to December. So notice that we have 11 months, okay, because you have to have one, you have to take out 1 month. Otherwise, regression will not, even if you put January in, it's not going to matter much. Regression output will just not give you any result for January. Because if you have 12 levels of a variable like month, January to December, you only need 11 binary variables to represent that 12 level variable of month. Quarters have 4 values, quarter 1, quarter 2, quarter 3, quarter 4, so you need only 3 binary variables. Day of the week have 7 values, Monday to Sunday. You only need 6 variables, 7 minus 1. So you only need 1 less binary variable than the number of levels you have. Okay, and then what you do is you go to data analysis, regression, and your Y value is going to be the sales. Okay, so that's going to be the sales values right here. I'm going to select the sales because I want the labels in my output. Okay, so select the sales values and you click labels, make sure it's checked. And then for the X values, you can select multiple columns. So I'll select time and my 11 months, February to December. And I want to go down till the end of the 4th year. That's all the data I have. Okay, you can do output in a new worksheet. Okay, and then hit OK. And so this is the output of regression. Okay, B0, that's the intercept. B1 times time is, this is B1. Then this is B2 for February, B3 for March, B4 for April, all the way down. And now you can see that the R-square value is 97%. So if you remember our slide, actually no, it's in Excel. So if you remember the data, notice with just the model capturing the trend, R-square was 33%. But now when I have done regression and I have gotten the output of regression with the seasonal factors, these 11 binary variables, my R-square has gone up to 97%. So now I'm capturing most of the variability in the data. So how do I use this regression equation to do my prediction? So the equation essentially is y of t equals b0 plus b1 times t, okay, plus b2 times Feb, plus B3 times March, and on and on and on until you get B12 times B12 times December. Okay, and so what I like to do is I take these values and I copy paste them where my data is. Okay, and I paste them here using paste special and transpose values. So I over time column I get the B1 for time, over February column I get the B2 for Feb, over March I get the B3 for March. You have to line them up, and over my Y variable this is just the constant B0. Okay, then to do my forecast, all you have to do is multiply, take the constant B0, then do plus this times time, B1 times time, plus this times this, plus this times this, plus this times this. Okay, a shorter way to do all that is to do sum product. So what I can do is I can say sum product of these red cells, comma, with these purple cells. So to multiply this times this, plus this times this, plus this times this, plus this times this, plus 284 times this, and so on. And then at the end, you want to add the B0, the constant, 669, or at the beginning. Okay, and I put dollar signs on these red boxes and this blue box. So when I drag the formula down, the blue and the red box stay locked, and the purple selector row moves down to give me a forecast for each row. So that's how I develop the forecast here for each row. Then I can calculate the error up to the first 4 years because I have the true value, and the squared error. Then I can calculate the MAD and the root mean square value. And if I just want the MSC value, I can just average these squared errors. Okay. So MAD, root mean square value, which is the mean square value square root, or just the raw mean squared value. So I can get this error. Now I can do the same thing to develop a forecast for the 5th year, which was being held out. I'll do the same thing. I'm actually going to done it right here because I don't have the sales values, but I have the time variable, I have the 12-month variable. So I developed this forecast right here using the same sum product formula that is being used on the last row. Same formula gets here to forecast for the next 12 months. And then I can just copy these values in front of the holdout sample here, calculate my absolute error, my error squared, get MAD and the root mean squared value, okay, which is square root of the MSE, or you can just square this to get the MSE value. And you can see that the MAD of 102 is much larger than the MAD of 32 here. MAPE here is 8%. MAPE here is going to be less than 8%. But what the holdout sample is suggesting is when you actually go ahead and use this equation to forecast, you're going to see some results more like this with a MAPE of 8 to 10% than very accurate results here, because here you're testing the model on the same data it was trained on. Okay? So that's how we can use regression, creating dummy or binary variables to handle seasonality using a regression model. Okay, so now that we know how to use regression to work with seasonal data, that has trend and seasonality, by the way, because this B1 term captures the trend, we're going to look at seasonal decomposition, where, remember with trend, what we did, we differentiated to take out the trend and apply simple exponential smoothing. So we're going to do something similar. We're going to take out the seasonality, leaving behind just the trend. Then we can forecast the trend using any of the trend methods we covered, like Holt's method, regression. And then we can re-season the data to get the seasonal pattern back in. Okay. So this way we can actually use regression for just a trend and use multiplicative seasonality, seasonal factors which are like a ratio, like a 40% higher sale or 20% higher sale. Because if you use the regular regression equation like this, we get additive seasonality only. Okay, so let's look at how to do this in Excel. It will be a step. Step 0, determine M, the time period for which the seasonal pattern repeats. For monthly data is usually 12. And so, we have monthly sales data, so M is going to be 12. Then we estimate the seasonal factor F1 to F12 for all 12 months. And you're going to see it's relatively easy to do that. We average seasonal factors for the first month, because we have multi-year data. You're going to get different values of F1 from each year. F1 is the seasonal factor for month 1. Then you average across them to get the average seasonal factor. Then you use those average seasonal factors to deseasonalize the data by dividing by the seasonal factor to get a deseasonalized data. Then you can use exponential smoothing if there's no trend, or a trend projection if there is a trend, like a regression line. And then you can re-seasonalize the data to get your forecast for the next year. So let's go back to Excel, and this is shown in the stepwise Excel sheet. okay, where you have your year, your month, your time variable, which keeps going up and does not wrap around after 12. You have your sales data. And then what you want to do is you want to calculate the average for each year, okay? And the way you can do that is using a pivot table. So I can look at the sales data and I can go to Insert, Pivot Table, and I want to do it in a new worksheet, okay? And I can drag my month, not my time variable, my month in the rows. No, actually, I need my year in the row. So that's the year column, and then I can look at my sales, and I can, instead of the sum, I can click in the values part. Instead of the sum, I can click and change it to an average. So that gives me the average for each year. So year one, my average sales are 977 per month. And then, you know, the average is going up. Then I can use these values to backfill this monthly average column. So the first year, all 12 months, the monthly average is the same, 977, which comes from right here. Okay. Okay, that's the year one monthly average. So that comes from here. The other way you could do it is you could just select these 12 values for year one and see the average is 977. Then type 977 here, copy and paste to get all the 12 values of year one. The average is 977. Then you can select the second year, the next 12 values, okay, and the average is 1059, and then you just type out or copy paste 1059 for the next 12 months. So for each observation, we need the value of the average monthly sales for that particular year. Okay, so all 12 values for year one will get the monthly sales of 977, average monthly sales. All values for year two will get the average monthly sales of 1059. And for year three, we can select the 12 values of the sales, and the average is 1168, so they get 1168, and so on. Okay. Then we take the sales and we divide by the monthly average to get the seasonal factor. This is my estimate of F1, my first seasonal factor in year one. F2, F3, F4, F5, F6, F7, F8, F9, F10, F11, F12. That's for the first year. Okay. Then we do the same thing for the second year. We divide the sales by the average monthly sales. And this is a second estimate of F1, the seasonality for the first month, from year two. So year one was saying that sales in January are 76% of the average monthly sales. But year two is saying that actually 70%. And then if you look at year three, it's saying it's actually 77% because there's some noise, there's some variability. Okay. So once we get all of these seasonal factors, what we're going to do is we are going to do it multiple ways. One is you can just say that the average, take the average of all the F1s, that's going to be this value here, okay, comma, then it's going to be month one again is right here, this value here, comma, year 3 month 1, this value here, and you keep going down, year 4 month 1, this value here. Okay. And if you take those average of those 4 F1 estimates from the 4 different years, you'll see that you get average of 0.74. So you put 0.74 as F1. The same thing for F2. Take all the 4 values of F2, okay, and find their average. Okay, and that's 0.71 month 2, 0.66, 0.68. Oh, I selected the wrong value here. So I need to unselect this and select this. And the average is 0.68. So 0.68 is F2. So you do the same thing for F3, F4, F5, F6, F7, F8, F9, F10, F11, F12. And then you just copy, paste, and repeat them. Then these values just repeat for the next 12 months, repeat for the next 12 months, and keep on repeating, because these 12 values right here are your estimates of the seasonal factors in your data. And they're going to apply to all the other months. So these are the 12 factors, F1 to F12. They apply again to year 2. The same exact factors apply to year 3, apply to year 4, apply to year 5. Now to deseasonalize the sales data, we take the sales and we divide by the seasonal factor. So this is the sales in January, what we would expect them to be if there was no seasonality. But seasonality in January is pulling the sales down to 742 instead of being 1,000. Okay, and whenever a seasonal factor is less than 1, it's pulling sales down, and whenever seasonal factor is more than 1, like 1.17, 1.24, it's going to pull sales up. Okay, so in the real sales, so these sales with seasonal factors above than 1 were pulled up from the monthly sales or the deseasonalized sales, and these sales were pulled down. So when you reverse it, the reverse happens. So when I deseasonalize the sales, these sales will go up because the seasonal factor is less than 1, so they will increase. So they would have been about 1,000, and these sales would decrease because they're already inflated by seasonality. So the uninflated sales are right here. Okay, and just about simple division of the true sales divided by the seasonal factor give you the deseasonalized sales. Now if you plot these deseasonalized sales, you get a plot like this, and you can see that seasonality has been removed. Compared to this, look at the extreme seasonality in it. Seasonality here has been mostly removed. Look at the R squared by just the trend projection, by the simple regression line with B0 plus B1T. You get R squared of 86%. Before, with seasonality, we're getting an R squared of 33%. So that means our deseasonalizing the sales has worked, and now we can project the trend forward. So we can use this equation, B0 plus B1T, to estimate the trend. And then once we forecast the sales based on the trend, then we can re-seasonalize the data. So the trend projection will be B0 plus B1T. You get the trend projection for all of the months. Okay. And then you simply multiply by the seasonal factors to introduce seasonality back into your data. Remember, we took seasonality out by dividing it. We reintroduce it by multiplying it because to undo the division, right? So we did the division with the seasonal factors to get rid of seasonality, and we projected the trend forward. Now we have to multiply, because we divided initially, by the same seasonal factors to get the seasonality back in. So we multiply by 0.74 for January. For February, we multiply by 0.68. Similarly, for June, we multiply by 1.13. Okay, and then once the first year is up, we again go back to multiplying by the same factor, repeat the same factors down. We adjust them in the same way. So this is my final forecast, which is the trend projection multiplied by the seasonal factor. And I can do this for future time periods, because I can project the trend forward using values of t. So it's B0 plus B1t. So I put a value of t to be 49, 50, 51. I can get the future values of the trend. And I'm going to introduce seasonality based on the same seasonal factors that I've calculated, the 12 seasonal factors I've calculated above. I'm going to reuse the same factors, and I have my projection. Now, let's look at the error, okay, for this training data set. Okay, so I'm going to look at the absolute error, and then I'm going to look at the error squared. The absolute error is absolute value. I take the true value of sales, and I subtract minus my forecast, okay, and then I can go down all the way till I have actual real sales data, and then I stop here, and then I say my MAD will be the average of these standard deviations. Okay. Okay. And if I look at my holdout sample, again, I project the trend forward and I then use the seasonal factors, multiply by them to get my forecast. And if I look at the 12 months holdout sample, my MAD is 139. And you can see the MAD on the training data is much lower. This is the benefit of doing the holdout sample, because I know that when I actually use this model, I should expect an MAD closer to this holdout sample and not such a small MAD, because I'm fitting to the training data, and so the model is not going to work as well on new data as it worked on the training data. Okay. Then for error squared, we can calculate the error, which is the true value of the sales minus the forecast squared. Then I bring it down, and then MSE is just going to be the average of these squared errors. Okay. And I can calculate RMSE, root mean squared error, which is just the square root of this number. Okay. And then you can calculate MAPE as well if you want to. You can add another column here where you take the error and you divide by the actual value to convert into a ratio. Then you average the ratio, multiply by 100 to get MAPE. Okay, and so that's how you can do it with the regression, with just the trend regression. When you de-seasonalize the sales, you take away seasonality and you put the seasonality back in at the end. This is sometimes called seasonal decomposition of the time series. It's also called like the stepwise method to get to your forecast. And that's the second method we have seen. The advantage of this method is that we are modeling seasonality as multiplicative, and the advantage of this method using binary variables for different months was that it's much faster to do. Just build your binary variables, just run regression, you have your forecasts. But the disadvantage is it assumes additive seasonality, and sometimes you want to model seasonality as multiplicative. Okay, so now we are going to do another example, and then we're going to do the Holzwinter method. Okay, this example is really simple. We have demand data by quarter, so quarterly demand data, and we are going to use like the stepwise method to find the seasonal indices, the seasonal factors, so we can project the sales forward and then kind of do the seasonal adjustment. Okay, so year one demand is given here, year two demand is given in this column. We can find the total demand for the year, divide by 4 to get the average quarterly sales. So in year one, on average, we are selling 250 per quarter. Okay. Then looking at the actual values and comparing them with the average sales for the year, we can calculate seasonal factors. Seasonal factors are simply the actual sales divided by the average sales per month, which is 250. And we get seasonal factors for year one. The same thing with year two. You take the year two's quarterly data, you sum it up, divide by 4. So in year two, the average quarterly sales was 300. You divide each of the quarterly sales values, each of these 4 values, by 300 to get the seasonal factors for year two. Same thing for year 3 and 4. Okay, and now for each quarter, you have 4 seasonal factors. Quarter one, your seasonal factor is 0.18 or 0.23 from year 2, or 0.22 from year 3, or 0.18 from year 4. So you're going to average these 4 seasonal factors for quarter one, which you got 1 per year for the 4 years of data to get the average seasonal factor. So average seasonal factor for quarter one is 0.18 from year 1, quarter 1, 0.23 from year 2, quarter 1, 0.22 from year 3, quarter 1, and 0.18 for year 4, quarter 1. Add them up, divide by 4, you get the average seasonal factor for quarter 1. Do the same thing for quarter 2, quarter 3, quarter 4, and you get these average seasonal factors. Now, because I have M is 4, I have quarterly seasonality, the sum of the seasonal factors should add up to 4. If it's not adding up to 4, you have to rescale it. So let's say the sum adds up to 4.5, then you divide each seasonal factor by 4.5 and multiply by 4, or in other words, multiply by 4 over 4.5 to scale them, so they should always add up to M. that is a condition you need. Otherwise, your seasonal factors will be capturing some other information like trend or something, because they will be inflating or deflating the sales over the year. We only want them to move the sales up or down over the months or the quarters, not the total for the year. So that's why we need them to add up to M. Okay, so you can just double check. They will usually, if you follow the process, but you should just double check to make sure they add up to M. Now that we have the seasonal factors, okay, the question tells us that year 5 sales are going to increase by the average increase you've been noticing. So year 1 to year 2, our sales increased by 200. Year 2 to year 3, our sales increased by 600. And year 3 to year 4, our sales increased by 400. The average of 200, 600, and 400 is 400. So the sales grows on average by 400 units. So my year 5 total sales, not quarterly sales. If I look at my total sales right here, year 4 total sales were 2200. So if I add 400 to this, I should get my total sales for year 5, which will be 2600. So because this is just, but the question is telling me to do this thing. Otherwise, you could just look at the annual sales and do a regression line, like a simple trend regression line, or you could do a exponential smoothing, because annual sales are not going to have quarterly seasonality. When you add up the sales for the 4 quarters to get annual sales, the seasonality has been removed because you summed up across all the quarters. So you can just project it forward by any method you want. The question will usually tell you what method to use. So one common method is to just look at the increase over the last years and just take the average of that increase and say it's going to increase by the average amount. So the average increase was 400 over the last few years. So we'll say, okay, year 5 sales will be 2200 plus 400, 2600. Now we have to break up the 2600 into the quarterly forecast, because 2600 is the annual forecast. Annually, I expect to make sales of 2600 next year, but what about per quarter? So I can just multiply the average quarterly sales for year 5 by the seasonal factor indices to get the sales per quarter. So what do? I take the annual sales of 2600, I divide by 4, and I get that 650 is the average sales per quarter over the next year that I expect. But I know that the quarters are not all equal. Some quarters are high, some are low. So I multiply the 650 by the 4 seasonal factors to get the forecast for each quarter. So we see quarter 1 is very slow, quarter 2 is picking up, quarter 3 is going the fastest, is a hot selling season, and then quarter 4 we come back down in sales. And all of this quarterly variability is captured by the seasonal factors, and I multiply them by the seasonal factor to get it. Okay, so this was an example of this stepwise method where you find the seasonal factors, you average them, you find the seasonal factors, you average them, and then you project the sales forward for the next year without seasonality, and then you re-seasonalize your projections by multiplying by these seasonal factors. So same thing has been shown to you here. Which this is a little bit more manageable because it's quarterly data. You don't have so many observations, and this is often I like to, if I put a question on the exam, I often use quarterly data like this because quarterly data is a little bit easy to analyze. Although you are supposed to use Excel, so even with monthly data, just drag the formula down. It's not a problem, but this is a good example to learn. Okay. Let's look at the last way of handling seasonality, which is the Holes and Winters method. It's very much like the Holes method. Okay, this one. In the Holes method, we had level L and trend T, and we would break up the sales into level and trend component and have alpha and beta smoothing factors to smooth the level and trend component. Then we would combine them again to build our forecast. It's the same idea, except we have 3 components of the time series now. We have a level component L, a trend component T, and a seasonal component S. And our final output is level plus trend times seasonality. So it's a multiplicative seasonality model. We're multiplying by the seasonal index to get our sales. So we'll break up our time series into 3 components, L, T, and S. We'll use exponential smoothing to smooth each of these components. We'll project them into the future and combine them to get a future sales forecast. what we do have to realize is when we are forecasting the future, okay, so YT plus 1 is going to be level plus 1 times trend times the appropriate seasonal factor. So it's not going to take, if YT plus 1 is March, it has to take the seasonal factor for March, not something else. So that's why this subscript looks a little bit confusing, but all it's saying is match the seasonal factor with the month you're forecasting for. It doesn't make sense, let's say, to be forecasting for June and be using a seasonal factor for January, right? So you have to use the appropriate seasonal factor. Okay. So let's see an example of the Holt-Winters method in Excel. Okay, so these are the equations. The level component takes the previous value of y and deseasonalizes it by dividing it by the most recent seasonal index for that month. Then it takes 1 minus alpha, takes the level and the trend combined from the last time period to add the forecast of the new time period for the deseasonalized sales, and then kind of combines the two with alpha 1 minus alpha. The trend component, okay, called B, is going to take the change in the level component plus the old estimate of the trend component. And the seasonal index is just going to take the old estimate of the seasonal index and smooth it with the new estimate, which is always the actual value divided by the level. And then the forecast for the future is going to be given by level plus trend times M, which is how many time periods in the future do you want to forecast. You want to forecast next month, and M is 1. You want to forecast the second month, M is 2. Forecast the third month, M is 3. And then we pick the appropriate seasonal factor for each month that we are projecting to. Okay, so the complicated thing about this, and you have the Excel sheet, so you can look at the formulas. A little bit complicated thing about this Holt-Winters is how do we initialize it, because these iterative formulas need an old value of level and trend and seasonality to update it. These are like updating formulas. So how do you have a starting point, some starting values of level, trend, and seasonality that you can start with and then use these formulas to update? So for the level, the starting value is simply the average of the first year. So the average monthly sales of the first year is going to be the starting value of the level going forward to year 2 onward. So the first year, we don't really build a forecast. We just initialize the algorithm. And from second year on, we start, updating our estimates and doing our forecasting. Okay. For the trend, okay, we can just, there's multiple things you can do. You can look at the first two, you can plot the values of the first 2 years and use a regression line to see what the slope is between year 1 and year 2. All what I'm doing here is I'm simply taking the same month of the next year and calculating the change, and that'll be an annual change like January to January, but then divide by 12 to get the monthly change. So from year 1 January to year 2 January, the monthly change seems to be minus 0.08. Then from February to February, it seems to be minus 0.25. At the end of year 1, I can just kind of average these trends that I estimated for the trend component and just use like the average. Okay, here. What I'm actually, so this would be for the 12th month, the estimate of the trend, and then I add to it the estimates of the first 11 months, and I multiply the whole thing by 1 over 12 to basically get the average. So 6.86 is the average growth on month-to-month basis over the first year. So second year on average is about 7. The change is about 7 or 6.8 units. And then to initialize my seasonal factors, I simply take the sales divided by the average monthly sales for year 1. So that gives me the seasonal factor for the first month. For the second month, again, actual sales divided by the average monthly sales for year 1. So once you initialize that, then you can plug in these equations, and I've already done it for you, so you can kind of reuse this Excel sheet or modify it however you want. And so just I put in these equations to project the trend and the level, the trend, and the seasonality forward. Then from year 2, I can start calculating the absolute error and the squared error. Okay, and then I can calculate MAD and MSE. And I also have this holdout sample. So anyway, then you just type in these equations to update the level, the trend, and the seasonality, and then your seasonality is here, trend and level, and then your Holt-Winters method simply takes the old values of level and trend and the old value of the seasonal index to forecast this value, because you don't know that the level and trend are going to be the same in you don't know these values of this of the level and trend for the second month, because these values depend on the sales of the second month, which you don't know. So this value, for example, depends on the sales 741. This value depends on this value, which depends on 741. So 741 is not reliable to use because we haven't observed it yet. We can't use it. We'll be looking at the future. So to forecast the sales of year 2, month 1, we have to build this forecast without looking at the 741. Okay. Then you can drag this formula down, all these formulas down, like this one down, and this depends on those, so this one down, to get the forecast. When you get to the end of the 4 years, to get the forecast for the next 12 months, what you're going to do is you're going to use this formula. They're going to take the latest level you have, the latest trend you have, times M, and then the whole thing times the latest seasonal factor. Okay, so you can notice we take the level and trend and we multiply by 1, because M is 1, looking 1 period ahead. Then you multiply by the most recent seasonal index for that month ahead, which is January, and then we develop a forecast for January, which is 1023. Same thing here, same level and trend. Seasonal factor will be for February, and you multiply by 2, which is right here, B53, 2, to get the 2 month ahead forecast. Okay. Now, we can calculate the error. We don't calculate the error for the first year. Why? Because we use the first year of data to initialize these parameters. So we can't calculate the error on the first year for this technique. The data that's used to initialize the system, we don't calculate the error on that data point. It's kind of like that data point got used up in making sure the system was bug-free. Okay, so the error simply is going to be the true value minus the forecasted value. Okay, so then we can calculate the MAD, which is simply the average of the absolute deviations, which is 38. We calculate the MSE, which is 51. And then we go to our holdout sample and we apply the same. This is our forecast for the holdout sample, because there's no observed Y for these time periods. And we'll compare this forecast for the next 12 months with the actual sales that we kept at the holdout sample for the next 12 months. And we see that MAD is 116, larger than what the training data would lead us to believe. This is why you should never rely on just the training data to see what your MAD, MSE in real life will be. For unseen data, you might get a higher MAD, MSE like the holdout sample shows you. This is a plot of the true values in blue of the sales and the Holt-Winters forecast in gray. And you can see how closely the gray is tracking the blue values, and then it's giving you a forecast for the next year, which looks very believable. If you just extend the pattern visually, you get this pattern for next year's sales forecasts. Okay. Again, you can access the Excel file, compare, see what's happening with the formulas, and then contact me if you don't understand something. Okay, so we have finished the seasonal forecasting. Okay, for this shampoo bottle example, we've done seasonal forecasting a bunch of ways. We did with regression, with binary variables for the months or the quarters, depending on your data, right? This was our first method. Then the second method, we manually deseasonalize the sales to get only a trend component left in the data. Then we can use regression or just the average change over the last 4 or 5 years to project the sales into the future. Then we bring seasonality back in by multiplying by the seasonal factor. So it's like decomposition, a stepwise method. And then we did the Holtz-Winters method, which is, you track the level, the trend, and the seasonal indexes, and you smooth them using smoothing coefficients. One thing I forgot to show you was we have 3 smoothing coefficients now: alpha to smooth the level, beta to smooth the trend, and gamma to smooth the seasonal time periods. And you'll notice in the level formula, we are using the alpha here. In the trend formula, we are using the beta to smooth it. And in the seasonal index formula, we are using the gamma to smooth the seasonal index observations. And smoothing means to average out the noise. Okay, so now that we've finished dealing with seasonal data, we're going to look at judgment forecasting. And this is a technique where you try to get information about the context, the business situation, the economy, and try to come up with a reasonable forecast. Okay, so it's kind of like your gut feel, and it's often used to adjust forecast from statistical methods rather than be a forecast on its own, because it is susceptible to human biases. But somebody might say, well, my Holt-Winters method is only looking at trend and seasonality in the past, but the business environment has changed, a new competitor has entered, something else has happened, so I need to adjust this sales forecast from the Holt-Winters method, and that's fine, right? Also, judgment forecasts provide contextual knowledge gained through experience. So often you might also ask your Salesforce people or marketing research people, executive opinion, and so on, and Delphi method to get opinion of experts to adjust your forecast up or down, that the forecast you got from the statistical methods. If you have no historical data, sometimes judgment forecasting may be used to get the actual forecast, not as an adjustment to a statistical forecast. So if historical data is not available, or something so drastic has happened, like something like COVID-19, which has changed the consumer behavior so much during the COVID pandemic, that you can't rely on the old historical data and you just have to use judgment forecasting because there's not enough relevant historical data available. Often we use it to adjust our statistical forecast up or down based on the business environment and other things. I want you to watch this YouTube video. The link is in the slides. And you can watch on your own time. And this is a video of Ellie Goldratt, who wrote the book called The Goal, which I like to have students read for my courses or for my operations course. He had a nice video where he is talking to some executives and how a recession is causing them to predict that their sales will fall by like 50% or something, but that's not true. And he uses judgment forecasting, like reasoned thinking, to help them get to like what they can expect to happen. So that's a very good example of judgment forecasting that you can watch in this short video. Let's talk about how do we select a forecasting method, right? So we talked about a lot of forecasting methods. Some handle trend and seasonality, like Holtz and Winters, right? So one way we need to, the one criteria we use is that the method we use must be able to deal with the components in the time series. If the time series has seasonality, just using the Holtz method is not enough. So you have to use Holtz and Winters to handle trend and seasonality. But let's say there's no trend and no seasonality, then maybe you can use simple exponential smoothing. Let's say there's only seasonality and no trend. You can still use Holtz-Winters that will estimate trend to be very low, or you can use the stepwise method where you deseasonalize the data. Then because there's no trend, you use simple exponential smoothing to project the data forward, and then you reseasonalize the data by multiplying the predictions by the seasonal forecasts. So depending on what components of the time series are present in your data, you have to pick a method which can handle those components. Then you have to pick the parameters like alpha, beta, gamma values, the smoothing coefficients. So if your demand pattern is not changing very quickly, it changes slowly, you should pick small values of alpha. And if you have more dynamic demand, like this, not just alpha, all the smoothing constants. And if your demand is very dynamic, like your trend is changing every 2-3 years, then you want to look, quickly adjust to those changes in your Holtz-Winters method. So you would use a little bit larger values of alpha and beta, and if your seasonality is changing a lot, of gamma. In terms of regression, if you have stable demand pattern, you'll pick a large sample size, go back a lot in the history, in the past, to get the large sample size for regression. But if you have very dynamic demand patterns, then very old values of your sales data are not relevant anymore because the trend has changed, the seasonality may have changed. So then in the regression, you don't want to have a big, huge sample size going back 50 years because a lot of the data is not relevant. And regression gives equal weight to each value. It's not like Holtz method or Holtz-Winter or exponential smoothing methods where the recent observations get higher weightage and old observations get low weight. In regression, all observations have equal weight, so you don't want to go back too far back in time if you have dynamic data, like the patterns are changing. The method should also minimize bias, which we showed you how to get with CFE. And then the method should minimize some error measure, MAD, MSE, MAPE, for the recent time periods. In regression, you can also look at R square. If your model has a high R square, it's explaining a lot of the variability in the data. Avoiding overfitting. Overfitting is a very important topic, especially when you're using forecasting with regression, because you estimate the regression equation over a certain set of data. That's called the training data. And then when you apply it to forecast for future, you are forecasting, if you're forecasting one period into the future, that's not a big issue. But if you're forecasting multiple periods into the future, you're using values of your variables in the regression model, but for the upcoming periods, but the regression parameters, the B values, B0, B1, B2, B3, were estimated based on the training data. And so what ends up happening is when you estimate a regression model on training data, the forecast over the training data is going to have small error. But when you use those B0, B1, B2, B3 values to forecast future values of Y with with values of the X variables like time, seasonality, or any other variables like price you've incorporated into the regression model, then you may be, those values of the X variables may not have been seen by your model before when it was being estimated. And so it often will perform worse on this new data where it was not, which was not used to estimate the regression parameters. Let me show you in Excel what I mean exactly. So if you go to the regression, these are our parameters, right? B0 is right here, 669. B1 is 8.59, multiplies the time. B2 is minus 78, multiplies the variable called Feb, right? These values were estimated using 4 years of data, using this data set. But now I'm going to look at these X variable values of time and Feb and March that I did not estimate the B parameters on, but I'm going to use those B parameters, regression coefficients on these values to make a prediction, which is right here, this prediction right here, okay? And so what can happen is that your MAD and MSE on the training data can be very small. Look at the MAD, is pretty small. But when you look at this forecast, and I have the actual sales values because I kept this holdout sample, these sales values versus these forecasts that we got, the same values that we got here, I just copy pasted them up. The MAD is 102. Look at the difference, 32 versus 102. So this is called the performance of the prediction model outside the training sample. So if you want to figure out how accurate your regression model is, you should keep some data as a holdout sample, estimate the B0, B1, B2 parameters on your training data, and then use those parameters to make predictions for the holdout sample, and then see how well those predictions hold. And you'll find that this MAD is a more reliable estimate of your forecasting error when you apply this model to new data. Okay, so that's how regression models work, and some other forecasting models work. You take a holdout sample, you take some recent values, put them aside, then on the rest of your data you find the regression coefficients, or you train your model, and then you apply this model which is based on the training data to the holdout sample, and whatever MAD, MSE, MAPE you get on the holdout sample, that's gonna predict how accurate your forecasting method is gonna be in real life when you try to forecast the future. Okay. But there's this concept is a little bit difficult to apply to methods like Holt-Winters, because Holt-Winters update their level, trend, and seasonality components whenever they see one new observation. So whenever they get a new value of Y, they're going to update their estimates of L, B, and S with these equations. Okay, so you can't really have a holdout sample in the traditional sense. These are more like continuously updating methods like the Holt-Winters method and the Holt method, because you can only really predict one time period into the future. This time period into the future you can predict. I can predict this one as well, but still using very old values of level and trend. Ideally, I would have observed some value of YT here, and I would have updated my L, my B, and my S using those equations, and then this forecast would be based on these values right here, right? So it's like a rolling method which keeps updating its state with each new observation of Y. So we can't really call this a holdout sample here, that the data for the 50 that I kept away from the model. What I'm doing is I'm using my L, B, and S estimated on the first 4 years of data, and then I stop updating them, and I just apply the same value of L, B, and S with the T equals 1, T equals 2, T equals 3 to get the next 12 months of forecast. So this is more like using Holt-Winters to do a long-term forecast rather than just a one-period forecast. So for the one-period forecast, my MAD was this, 38, but for a 12-month ahead forecast, my MAD goes up to 116. So you can see the longer you forecast outside your data set, the more error your forecast is going to have, which is what shows up in Holt-Winters. So actually, if you actually apply Holt-Winters on this data set, it wouldn't work like this, because as soon as you observe the actual sales of 1030, right, you can now update these parameters here. Okay, and then this 963 would change. So as soon as you observe January of the 5th year, the sales, the forecast for February would change. So this green forecast here is not really a 1 month ahead forecast anymore. It's up to a 12-month ahead forecast, 1 month ahead, 2 month ahead, 3 month ahead, right? And so this is not really a holdout sample, because I'm not updating my L component, my B component, my S component. L is level, B is trend, S is seasonality. I'm not really updating them. So this is more like checking how Holt-Winters performs when forecasting multiple time periods into the future. Whereas with regression, I can have a holdout sample, because in regression, once you estimate the regression equation, okay, I can now apply it to the holdout sample. Now, obviously, in real life also, every few months when you get new data, you may want to rerun the regression and update those regression coefficients, right? So what you might say is, okay, well, my holdout sample performance is pretty poor, but up to 2 or 3 months ahead, I'm not doing that bad. So every 3 months, I'm going to rerun the regression and update my regression coefficients. And in real life, what you may also want to do is maybe throw away some of the very old data, because you might say, well, very old data is not really relevant because things are changing, and regression gives equal weight to each observation, even if it was very far back in the past. So you might throwing out old data, and you might start adding new data here to update your regression coefficients. Okay. But the key idea that when you estimate the model coefficients over some set of data, the model will do good on that data. But when you try to predict outside the training data, it doesn't do as well. A case where it often happens is, let's say you are changing your alpha, beta, and gamma parameters, the smoothing coefficients in the Holt-Winters method. And you keep playing with them until you really get a small MAD value here, okay? You get a very small MAD value here. So if you find the optimal values of these smoothing parameters. Now, when you go outside this sample, the values of alpha, beta, gamma that were optimal for this sample may not be optimal for new data. So that could be called overfitting. So you were really able to get a small MAD value because you picked smoothing coefficient values that were just that work well for this sample, but that may not work well on new data. So that could be an issue that you can check with a holdout sample. In that case, when you do run the holdout sample here, you would not change these smoothing parameters, but you would let the level component and the trend component and the seasonality component to update. So you would not be forecasting 12 months ahead. You would forecast 1 month ahead, then update LBS, forecast 1 month ahead, update LBS, but you would keep the smoothing coefficients the same, and that would be checking whether your smoothing coefficients that you optimize for the training set also are okay for new data. Because sometimes you can over optimize these smoothing coefficients. That's why I don't recommend you play with them to death until you really get a small error. Just find reasonable values for them that make sense, okay? And then just use them. Or if you do optimize them, then check them, then apply the algorithm with those smoothing coefficients on a new data set, on new data, and see if you're still getting a small value of MAD. Okay. So there are two issues here. One is a holdout sample, which tells you whether you have overfitted the smoothing parameters or not. And the other issue is if you forecast more than 1 month ahead, how does your forecast error change? In both cases, if you over optimize your smoothing coefficients or if you forecast too far ahead, your error will increase. So here I'm showing you forecasting 12 months ahead without updating the level component and the trend component and the seasonality component. Okay, and so if you keep these components the same and you forecast far ahead in time, your MAD will get worse. And also, if you over optimize these on a training data set, then on new data, your model may not work as well. And in regression, the same point. If you estimate the regression coefficients over a data set, the regression model will not perform as well on a new data set as it did on the training data set. But you can always update, as you get new data, you can always update these regression coefficients so that you keep a good level of performance in new data as well. So you have to rerun the regression then. Okay, so that is the idea of forecasting into the future and using a holdout sample. Because when you really optimize your model to predict on a training data set, you get good performance on a training data set. But if you forecast more than 1 month out, or if you get new data and your model parameters were optimized for the training data, your performance can degrade. So that is this idea of avoiding overfitting. It applies very cleanly when you go to more machine learning approaches, but it does also apply when you are estimating regression coefficients. It does also apply when you're putting those smoothing coefficients, alpha, beta, and gamma. So something to keep in mind, and something to keep in mind that you may have to recompute your regression coefficients as you get new data, and you may have to readjust your alpha, beta, gamma if they were too optimized to the training data set. Now we're going to talk about forecasting as a process. How do we manage the forecasting process in the organization? So forecasting is a cyclical process. You keep repeating it. So let's say you develop a forecast for the next 6 months. Then next month, when you get some new sales data, you should revise the forecast. Okay, so that's why cyclical. You keep doing it every week or every month. You keep revising the forecast for the future as you get more sales data, as you get updated and new sales data. Multiple forecasting methods can be used, and then they can be combined. So people have found sometimes that instead of using just one method, use regression, use Holt-Winters, and maybe take an average of the forecast you get from both. That might work better than just Holt-Winters by itself or regression by itself. Okay. That's called combination forecasting. And then focus forecasting is what we've been doing. We just pick a method and we stick to it. And focus forecasting would be you test multiple forecasting methods and then pick the one which works best for your data. Okay. And then you can apply that going forward. And you may also want to adjust the output of statistical methods if the business environment is changing and the statistical method is not incorporating that, then you may want to manually adjust it. Okay, so let's look at some more forecasting process considerations. In make-to-stock environments where you are building product in anticipation of demand, you need a forecast for each SKU, right? Because you have to figure out how much of each SKU to produce. These are environments like retail where customer, when they place an order, they're not going to wait months for you to go and make that product. So individual SKU forecasts can be rolled up or aggregated to get product category and company level forecast. Since aggregate level forecasts are more accurate, you can compare these rolled up forecasts with a forecast built with aggregate data. Okay. And then you can also disaggregate aggregate forecast to get SKU level forecasts. Based on a predicted product mix or ranking, like top 10 SKUs will give you 20% of the sales. So when you do it both ways, you do SKU level forecasting and you roll it up, or you do aggregate forecasting and you roll it down. Doing it both ways will help you see where the discrepancies are, because often SKU level forecasts can be too optimistic, but when you add all of them up, you find like a really unreasonable value for this company's sales. Let's say they show the company sales needs to grow by 40%, and you know you're not going to grow by 40%, and so then you can kind of reduce the SKU level forecasts. In make-to-order environments, it's often sufficient to forecast resource requirements, like how much labor do you need, how many raw materials do you need, because you don't need to forecast exact SKUs, because as long as you have the raw materials on hand and the labor and the machines available, when the order comes in, because in make-to-order, you produce after getting the customer order. So once the order comes in, you have everything ready, capacity is there, workers are there, raw materials are already been sourced, you can quickly produce and ship it out. So in make-to-order environments, it's easy because you don't have to focus at the SKU level. You just focus, okay, your labor requirements, like how many labor hours have you been needing in the last 12 months or last 2-3 years, and then you forecast that using some statistical methods to get a forecast of how many labor hours you'll need in the months to come. You can also try to forecast the number of orders you'll get and then kind of work back into labor requirements. Or you can just forecast, things like labor requirements, raw materials directly based on historical data. But you don't have to go to the SKU level, which is nice. You can just work at the aggregate category level forecast. And for this category, you need, these raw materials, these workers on hand, and these machines on hand, and so forth. Now, if you were, let's say, using some forecasting method, let's say you're using regression to take care of trend, and then the trend might change. So you need something in the forecasting process to point out to you that whatever forecasting method you've been using, things have changed and it's not working as well anymore. So maybe you want to revise it. So how can we get that? So you might have seen control charts in quality management. We can use control charts the same way using a tracking signal. And the tracking signal is basically just the cumulative forecast error at time t divided by the MAD for that time t. Okay, and that's called a tracking signal t. And then you can plot it and kind of use control charts to see where the tracking signal goes too high. Because what does it mean? If this when the forecast method stops working, like let's say the trend changes, you'll start to get bias in your forecast. CFE measures the bias, but how much bias is too much? If on average you make an error of, let's say, 50 units, that's MAD, and if CFE has gone above 50 units by a lot, like CFE is 250 or something, that means you have a lot of bias in your forecast. CFE is very high, and CFE over MAD, that tracking signal will show you that CFE is too high. Okay, and so when you the tracking signal goes too high or too low, it could be positive or negative bias. You know that something has gone off, and you have to review the assumptions of your forecasting method, see whether the trend has gone away, you don't have trend anymore, or if the trend has changed, or seasonality has appeared or disappeared or changed in some way, and so you need to update your forecasting method because the current one has bias in it. So the major advantage of tracking signal is that it detects bias. Even if bias is small, it adds up in the cumulative error. The major disadvantage of the tracking signal is that large positive and negative errors can average out because you use cumulative error. So if there is no bias, even if your errors are just growing more, you have a lot of variability in your errors. Your errors are going large or small, but there's no bias in them. It may not detect that your errors have grown higher in magnitude, but MAD, like a rolling window MAD and MSC, will detect that. Often we use 3 sigma limits for the control chart. Because the tracking signal's expected value is 0, we do 0 plus 3 sigma and 0 minus 3 sigma to find the control limits for the tracking signal. Okay. Well, how do you find sigma? Sigma is simply the square root of the MSE. Okay. If you are given the MAD is square root of pi by 2 times the MAD, which comes out to approximately 1.25 times MAD. So if your MAD is 10, then your sigma is going to be 12.5, 1.25 times 10. Once you have sigma and Z's, you're going to use 3 sigma limits usually. You're going to go to 0 plus 3 times sigma as the upper control limit and 0 minus 3 times sigma for the lower control limit. And as long as your tracking signal is within these control limits, you're kind of doing fine. If your tracking signal exceeds these control limits, then you have bias in your forecast and you need to reevaluate your forecasting process. This is an example of that. These are control limits. You can see they should be centered around 0. Okay, so this is an example of a control chart. So you can see centered around 0, plus 3 sigma upper control limit, 0 minus 3 sigma lower control limit, and this is your tracking signal. And things were going fine, but something happened and the tracking signal just shot up, and so that's showing you that you have a lot of bias in your forecast now, and something went wrong. Either your trend changed or something changed, or somebody just used the wrong formula. Somehow your forecast just went worse recently, so you need to investigate that. Yeah. These control charts to look at the tracking signal are especially useful if you are using some automated forecasting process like ERP systems like SAP. They may have automated forecasting where you pick an algorithm and it just automatically keeps updating the forecast as new sales data becomes available. In those sort of situations, you may want to have tracking signals in place. So if your forecast goes off, you can kind of go back in and see, okay, what happened? Maybe the data has changed and the forecasting algorithm you're using doesn't deal with this new issue, or something in the business environment has changed which is causing your forecast to be wrong, and maybe you need to use judgment forecasting to adjust for that. But in any case, this shows you need to investigate the issue and resolve it because your forecast is having too much error now. So you can use control charts to keep track of the forecasting process. Okay, so if you have any questions, you can reach out to me.